Alright, hello retards. So right now I'm gonna go through the exam review really quickly. This is my first time doing it, so maybe I'll make mistakes, maybe not. We'll see. This is not meant to teach you. This is not a lecture. This is not a lesson. This is just you confirming your understanding and confirming your answers. Okay, so I'm gonna go right into it. Convert decimal number -15 to 2's complement. Now we know in 4 bits you can store 15, but you cannot store 2's complement 4 bits of -15. You have to store it in 5 bits. And so what we'll have is 5 bits. So 0, 0, 0, 0, 0. That's 5 bits. Now let's get 15 using 5 bits. That's 0, 1, 1, 1, 1. How do I know this is 15? Because 1, 2, 4, 8. You add these up, you get 15. Right? Now perform 2's complement because this is positive 15. Turning this into negative, I'll get 0, I'll get 0, 0, 0, 0, 1. Then I'll add 1, so 1, 0, 0, 0, 1. Okay, so this is -15. And if you want to confirm it, you could always do 1, right? 1. This is 2, but since this is the 0, the 2 doesn't matter, the 4 doesn't matter, the 8 doesn't matter. This is -16. And so you add it up, -16 plus 1. Why is this -16? In 2's complement, your leftmost bit is always negative and everything else is positive. This is -15. Alright, now convert decimal number -7 to 2's complement. This we can do using 4 bits. There you go. And so doing this using 4 bits, what we'll get is, 7. So this is 1, 2, that's 3, 4, that's 7. So 1, 1, 1, 0. This is 1, 2, 4. Wait, no, I messed up. 4, 6, 4, 5, 6, 7. Oh no, I didn't mess up. What the fuck? Okay. Oops. So now performing 2's complement. And then you gotta add 1. How do you confirm this? This is -8 plus 1. That's -7. Alright. Let's move all this stuff away. Alright, now convert 2's complement binary number to a decimal. So you'll do the same thing. 1101. This is 1. This is 2. 2 doesn't count because it's a 0. So 4. And since this is 2's complement, this number is negative. And so -8 plus 4 is -4. Plus 1 is -3. Alright. Now let's do that again a couple more times, 2 more times. Convert this. What is this? 8 bits. That's 1, 2, 3, 4. 1, 2, 0, 0. Convert it. This is 1, 2, but they don't count because they're zeros. So we skip them. 1, 2, 4, 8, 16, 32, 64, -128. All right, now adding them up, I go what? 60, 64 plus 32, that's 96. 96, 106, 112, 120, 124. So this is what, -4? Yeah, I think -4. Okay. 2's complement here. How many bits is this? It's 6 bits. 0, 1, 1, 0, 1, 0. And so we get is 1, 2, but 1 doesn't count because it's 0. So 2, 4, 8, and this is 2's complement. And so you still do, what do you call it? 2, 8, 16. Yeah, so this would be -16. I believe, actually, I'm not too sure. That's actually a really good question. Huh. I don't know. Actually, well, if I had to invent 2's complement right now, I would say that the leftmost bit is always the -32. So I hope I didn't get this right. So 0, didn't get this wrong. 0, 1, 0, 1, 0. So this is 1, 2, 4, 8, 16, -32. This is 0, cancels out. This is cancels out. This cancels out. 16 plus 8 plus 2 is 26. Determine if the Boolean expression this is satisfiable. So this one, because it's 2 inputs, A and B, what you want to put is 0, 0, all the combinations, right? And so doing this, you got to plug them in here. And so is this satisfiable? Well, if we plug in 0, 0, this would not be it. This would be 1, 0. That's still not it. So here, actually no, yeah. So this would be 1, 0, which is still 0. Yeah. So this is our out. would be 0 here. And then here it would be 0, 1, which is obviously 0. And then this is a naught. And our 0 here, we naught it, it becomes 1. B is 1. This is satisfiable, so this is 1. And as soon as you get 0 and 1, that's satisfiable. Going to the next one here. This one has a C. It just means we add one more. And so adding a C, let me reorganize my bits. And so I'll get 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. I believe that's all the combos you get with 3 bits. Okay, so 0, 0, 0. Well, the thing is, we know if we even ignore this side, if you ignore this whole thing and only about your C, well, because here it's a C naught, that's a 1. And then because here it's a 1, that's a 0. Therefore, it's satisfiable. Right? Determine the pair period, assuming it's even. So if it's even, you get a 0 here, you'll get a 1 here, and you'll get a 0 here. Detect error, assuming even parity. Well, assuming this even parity, this is already even. This is odd, and this is odd, so this must be the one that's wrong. That's supposed to be a 0. Okay. Given a circuit composed of basic logic gates, determine if the light connected to the output is on or off. Well, this is a not, so here you'll get a 0. And since this is an AND, this is off. Here, what do we have? We have an OR, so either one of them has to be true. This is an XOR, and an XOR is only true when they're either or. And so this would give you 1, and this would give you the opposite of OR. And so if it's 1, 0, then this would give you true for OR, therefore false for XOR. This will be 0. Okay, let's see here. This is an AND, so this usually would give you 1, but since it's a NOT, it'll give you 0. And this will usually give you a 1, so that's a 1. And since it's 1 and 0 into an XOR, that's a 1. This is an OR, 0 and 1, this gives you a 1. Therefore, this is on. What is the largest number that can be expressed using 4 unsigned bits? So if they're unsigned, you get 8, because 2 to the 4 is your answer. Is that 8? 2 times 2 times 2 times 2. This is 4, this is 8, and this is 16. Okay, so it's actually 16. What is the largest number that can be represented using 4 unsigned bits? 16. But that doesn't make sense. Because if you're using 4 unsigned bits, that's 1, 1, 1, 1, which is 15, 8, wait, sorry, which is 8, 4, 2, 1, and that's what? That's 16, right? Am I tripping? This is supposed to be 15. 6 plus 8, yeah, that's 15. Yeah, so this is the largest number you can express in 8 bits. And sorry, 4 bits. What is the largest number that can be expressed using 4 signed bits? So if you use if it's unsigned and you can represent 15, then in signed you can represent half of that, because you have to cover the negative and the positive. So what you'll get is from -7 to 7. And so what is the largest number? 7? Well, something doesn't add up here, because 7 and 7 is 14. We're missing 1. Yeah, so it would actually be from -8 to 7. And so the maximum number is 7. What is the smallest number that can be expressed using 8 unsigned? Well, that's just 0. Right? 8 bits, because that'd be just 0, 0, 0, 0, 0, 0, 0, 0. What the fuck? He's trolling you. Alright, next question is rank the following memory option from fastest to slowest. And that is funny because he actually put them in order. So usually what you have is you have your CPU, and inside here you have your register, which is the fastest. Then your CPU connects to your RAM, right? which is bigger than your register, but it's slower than your register. Your register is faster, but it's smaller. Your RAM is bigger, but it's slower. And then this will connect to your hard drive, which is the biggest and the slowest. So this is 1, this is 2, this is 3. Which level of the cache is the fastest? So you get L1, which is the fastest, L2 second fastest, and L3 is the third fastest. Given the circuit below, which input values previous outputs? What will be the outputs after next clock high cycle? Next clock high cycle means it's 1. And so 1 and 1, this will give you 1. 1 and 0, this will give you 0. Right? Now, if this was 1, this is 1 and 1. And this is an OR. An OR will give you a 1, but since it's a NOT, this will give you a 0. Okay? And so that means this stays a 0. And now 1 and 0 will give you, well, this is an OR, and this will give you a NOT. Wait, something's off here. Actually, no, I am right. Yeah, so this would be, and then 1 and 0 will give you 0, right? This would go here, and then it'd be 1 and 0, and that would get, yeah, that would give you 0, and so this is undefined. You get both of them the same, it's undefined. For each of the assembly instructions below, indicate what the CPU will do as a result of the instruction. Mul. Now, a mul will do RAX equals RAX times whatever your register that you gave, which is RCX. Divide, RCX will do signed. So this is signed. We'll divide RAX equals RAX divided by RCX. Yeah, just don't forget that this is signed. JGE, and so this will jump to label if, well, actually, yeah, so jump to label. The other way you could say it, it's also, this will say, actually, I'll keep that. I'll write it 2 ways. But we'll jump to label if whatever this means. And I believe this one is the less than equal to or more than equal to. You guys can confirm what this actually means in one of my lectures that I just posted. But I think it's more than equal to. So this would be if A more than or equals to B. And yeah, so it would jump to the label if this. Or the second way you can say it, changes PC pointer to label address, but yeah, I would say this is a little bit harder for you guys to say, so this is much better. It will change PC if A more than or equals to B. Okay, compare RAX and 10. This will compare, obviously, compare RAX, compare value at RAX to 10 and set flags accordingly. Is he satisfied with this? I'm not sure. Because whatever the comparison, it will set flags, and then whatever comes after it will check those flags. Now, jump RPX is the same thing. Jump to instruction at RBX address. So RBX is holding some address, and when you jump to this address, when you jump to RBX, then you're going into this address and you're seeing whatever instructions is in there, and you're gonna execute it. Okay, and now we are into hacks, which is my favorite part and most people's least favorite part. Okay, load 0C. Now the easiest part here is you can basically just read this. So you see mar takes an address, and so OC, and let me make this a thicker pen. Yeah, that's good. Now 0C, which is here, this will go into mar, but not the value, the address, and so this would be 0C. Initial, yeah, initial is whatever, nobody cares what the initial is. So yeah, so this is 0C. Then the value at mar will go into the MBR. So here we'll have 0, 4, because that's the value now. This holds values, this holds addresses. Okay? And then after that, my MBR will go into my A. So my 0, 4 will go here. And then my PC increment, so my PC was 0, 0, becomes 0, 2. And then my IR gets whatever is inside my PC. And so, wait, I'm kind of confused here. Oh yeah, so this, yeah, so the IR will get the instructions of this. So this instruction is associated with 21. This instruction is associated with 10, and they give it to you. And so here will be 10. But for this step, so this step will stay as 21. I don't know why they have it here. It would stay 21. With this increment here, I'm trying to see how they want us to do the hacks. Does it update here and I write it here, or does it update here? But I'd assume it updates here actually, so this would be 10. I think that would be the right way to do it. And then they're asking, what's in your BMC? Well, whatever's up here, so we don't know yet. Right? And then here, we haven't changed any of these memories. They all stay the same. And now A goes into B, and so A stays the same here. But A goes into B, and so now B holds A, right? And then PC increments, and so this I still don't know. And this becomes 0, 2. My IR now has 21, which is the next instruction. PC. I still gotta confirm if they want us to do the instruction on the line or the next instruction, but I have a good guess it's the next one. Anyways, yeah, so I messed up. This is supposed to be 4 because you increment by 2, and this becomes 21. And as you can see, load is 21 and load is 21. That's how you know this is what the IR is. And anyways, so what does my mar hold? We still haven't changed our mar, so it still holds my 0C, 0, 4, my 0, 4, my FE, and my 0, 0. Now for the next step, we have 0D goes into mar, so mar takes 0D. And then member takes the variable at 0D, which is FE. Then FE goes into MBR, goes into A. Then my PC increments. And then the new instruction is what we get, which is 40. Everything else stays the same. I still don't know what my C is. I haven't changed it. And since in the beginning was nothing, it stays the same. I have not changed it. I have not touched it. And therefore, B also stays the same. Next step, now we're doing A plus B, and we're adding that into A. So B stays 4, and then we're adding A plus B. We're doing FE plus 4. Now, this is an N hex. So FE and hex, if I can remember, 15 and 14. This is 15. This is 14. So in case you guys didn't know, if you wanna, the way you can add these, I know this is 15 and 16. The way we can add these is, actually, hold on, whoops. So we have FE plus, what it's saying is AB. So B is C 0, 4, and A is FE. So FE plus 0, 4, right? And the way you do it is, well, E is 15. No, sorry, E is 14. And so 14 plus 14 is 18. But hex is base 16. So what you do is you split this into 16. So 16 plus 2, right? Now 16 I'm going to take up here. And so 2 stays. And then now I have F. F is 15. Plus 1 is 16, right? And so 15 plus 1 is 16 plus 0. This is just 16. But 16 is not a number, so I can do 16 plus 0. 0 goes down, and then 16 goes up as 1. And so this is 102. All right? Now here, it's technically supposed to be 102, but I think something to do with overflow that I do want to ask the prof about, but I don't think I got time for that. I think here it's supposed to be 0, 2. Just looking at everything, since it's just taking 2 positions, I'm assuming you can't take more than 2. That's why everything is in 2s. And so I'm gonna ignore the 1 as overflow and just keep the 2. Yeah, so usually for this, if there was a flag, you would check the flag for overflow, but in this chart there isn't, so I guess not. Anyways, C stays the same. EC increments to 8, and IR goes to 31. My MAR stays the same. My member stays the same, and my OC stays the same, and this stays the same, and this stays the same. All right. Now what we gotta do is MAR gets 0, 2, so E0E goes to MAR, which is here, right? And then MBR goes into A. Well, A goes into MBR, so A02 goes into MBR. And now MBR goes into MAR, so MBR goes into MAR. But remember, this is square brackets, so it goes into the address of 0A, which this is 0A, right? So this actually goes here. Okay, and so 0, 2. And then we increment PC, which you get 10. And 10 in hex is just A. So it's what, 0A? I would assume this is 0A because this is in hex. Then my IR increments and this 0, 0, right? And then here, I still don't know what my C is. We have not touched it the whole way. This stays at 0, 4. This stays at 0, 2. This stays at 0, 4. And FE. Now here, halt. Halt just means the CPU stops executing. However, these values stay the same. Values stay where they are. So all it does is it pauses the CPU. That's what halt is. It pauses the CPU. And that's the midterm practice. I'll do the assembly in a bit.